Before we move forward, we like to take a slight deviation and discuss the broad difference between Newtonian fluids and non-Newtonian fluids. Right in the beginning of this course, I did mention that Newtonian fluids are generally could be discussed as the fluids that follow the Newton's law of motion, the second laws of motion. And non-Newtonian can be described as the ones where the second law of motion is not applicable, and we have to consider some other forces, some other also parameters that come into picture, and we have to consider them as well. So the broad term, so these terms, but so there are few terms that we need to define and need to draw your attention to. This thing is also, well, we start with the rheology. What is rheology or rheological fluids or rheological motion? It is related to the study of deformation of flowing fluids. So you know that when a fluid is viscous and we try to deform it, the shear forces, stress forces comes into picture. And therefore, rheology is a subject that deals with that category of fluids. Newtonian fluids, for which the shear stress is linearly proportional to the shear strain. Now in this category, as I said, the Newton's law of motion will be applied, and in this case it is assumed that the shear stress is linearly proportional to shear strain. This is an important difference, and in rheological condition motion, there is no such condition of this linear proportionality relation between the stress forces and the shear strain forces. Newtonian fluids is not, this should be non-Newtonian fluids. I think for some reason we forgot to write that. Non-Newtonian fluids will be fluids where the shear stress is not linearly related to shear strain. So these are, remember, non-Newtonian fluids, whereas Newtonian fluids will follow the linearity law. Viscoelastic fluids. So which means that fluids that exhibit the properties of viscosity as well as elasticity. Viscosity will means that when we try to deform the fluid exhibit or tries to sort of react to the deformation or demonstrate a resistance to that demonstration. But otherwise, if it shows no resistance, then such fluids will be non-viscous, and in which case they deform as they want, such as we can give the example of water or most air or that kind of fluids. But in case of viscous and for elasticity are the fluids that which we try to apply a motion or a force, and after applying the deformation it comes back to its position. So it's kind of showing a property of elasticity as we observe in case of things like rubber. If we stretch it, it comes back to its position. If there is a steel wire or something, we apply a force, there is a strain, and if it comes back, we say that the particular item is elastic. So viscoelastic means a fluid that is exhibiting both type of properties that involve viscosity, the viscous fluid, as well as that of the elasticity that is coming back to its position. Trying to show the same things in a diagram, because sometimes the diagram, the graph reflects the same principles in a very decent way. And as they say that one picture is equivalent, can be equal to 100 pages of explanation at times. That kind of proverb says. So the same thing here, many things are combined in which there are, you can see the behavior of a shear thickening or Newtonian shear thinning and Bingham plastic type of fluids that show this behavior. If we see their behavior with respect to the shear stress and the shear strain rate. So that is the sigma, the relation between sigma and tau. And of course the pressure is there. So you can see that in case of Newtonian, we see a straight line. A straight line reflects a sense of proportionality. So that means that shear stress and shear strain are linearly proportional to each other, and as shear stress and this shear strain increases, they move linearly. They increase also linearly. But you can see the shear thickening of a fluid or shear thinning of a fluid is, they are not linearly dependent on each other. In fact, they behave differently, as you can see. So therefore, nonlinear terms will appear in that kind of motion. The example of fluid where shear thinning takes place, for example, there can be many, but I give you one simple example. The paint oil. The paint oil that we paint on walls or steel gates or that kind of thing. So what we call as oil paints. If we try to draw some oil paint together, then you see in the beginning it is quite viscous. But when we take a brush and we try to paint the same oil on a wall or on a gate, then there is a very thin film that is lying between the brush and the wall. And that thin film, it thins out so much that it does not remain as viscous as it appeared to be when there was a collective quantity of the oil paint. Similarly, there are a number of shear thickening examples also of the fluid, and Bingham plastic is a case where we need some finite stress to be applied to the fluid before it can start even to flow. Otherwise, the fluid does not even flow. So certain amount of force has to be applied, and that is why you can see that this kind of fluid start from a certain point of shear stress before they start moving. So shear thinning I have already mentioned and tried to explain to you, and plastics are those fluids in which the shear thinning effect is extreme. So it does not almost kind of take place, and in fact you know that in a elastoplastic material, the behavior of plastic is different from the behavior of the fluid, and in fact it does not follow Newton's laws of motion in totality. And shear thickening fluids or dilatant fluids, the more fluid is sheared, the more viscous it becomes. So these are the fluids that are shear thickening fluids. And when someone falls into quicksand, which is a fluid in the same category as mentioned above, then in fact the more he tries to move, he gets into more viscous fluids. But all this explains that there are different types of fluid motion which behaves in a different way depending upon the levels of viscosity and also depending upon their behavior with respect to shear stresses, shear strains and the relation, and we try to show that in the graph that I showed you earlier.